Ladies and gentlemen, welcome back to Mr. Lee physics class. So today we are going to learn the Doppler effect. So today's lesson objective. The aim of the study is to study and understand the Doppler effect. And lesson objective. In this lesson, students describe quantitatively the Doppler effect of sound, derive the expression for the frequency of sound when the source is moving towards and away from the stationary listener. Derive the expression for the frequency of sound when the listener is moving towards and away from the stationary source. And also understand the movement of the source will affect the wavelength of the sound. And last, use the derived formula to calculate the frequency of the sound. Ladies and gentlemen, to allow you to continue this lesson, assume period knowledge, for this lesson are students should already be familiar with the progressive wave. Second, the equation, the wave equation, that is V equal to F lambda, the bits concept, principle of superposition of waves, and the relative motion. Introduction. The animation show a racing car passing by at high speed from the viewpoint of the person holding the checkered flag. We also hear the distant sound of the engine as it approaches and passes. So now let's hear the sound produced by the F1 when it's approached to the observer and away from the observer. Again. The pitch of the sound, this means that the frequency of the sound is higher when the car is approaching than the car has passed. This phenomena is known as the Doppler effect. It's due to the motion of the approaching car and not because of the sound coming from the engine that has changed. So these are the objective of this lesson. Next slide. Let's say we have a stationary ambulance where the sound produced the speed of the car is 0 km/h and the sound produced will be like that. Please observe the wavefront for left, right, above, and below for all of the direction. All of the wavefront with the constant wavelength or same wavelengths in every direction. Now, let's say if the speed is moving with 50 km/h, the car, the ambulance move with 50 km/h. Again, please observe the wavelength of the wavefront for the left side and right side. That means the front of the ambulance and the back of the ambulance. We notice that the wavelength at the front part is shorter. Shorter wavelengths means that the frequency will be higher. How about if the ambulance moves with 100 km per hour? We observe that the wavelength in front of the ambulance is much smaller than just now. Now we notice that the wavelength behind the car will become much bigger. Then what will happen if the ambulance move with 50 km per hour in opposite direction? Just now move to right side, now move to left side. Again, we notice that no matter how, the wavelength of the sound wave of the siren will be shorter in the direction which the ambulance is moving. That means that in the direction of the ambulance, the sound wave will become much higher frequency compared to opposite direction. Next slide. Now we observe that if the ambulance produces a sound wave where the ambulance in the stationary position, means that the sound source with the station in the stationary position. That means that the speed of the sound for every direction, for left, right, above, okay, for all of the direction are constant. Where the wavelength for the sound are always constant for all of the direction. If the ambulance or the sound wave are in stationary state. Now, let's look at the diagram. There is an ambulance and there is an observer. Just now, the sound produced where the sound is heard by the driver in the car. Now, the ambulance produce the siren sound, and the sound wave is here by the observer, which stand with a distance, okay, with a distance from the sound source. Let's say stationary sound source. The sound heard by the observer will be the original sound by the siren because the wavelength are constant and the frequency are constant. Now, what happens if the ambulance moves with 50 km per hour? We notice that the frequency of the sound heard by the observer will become higher. Why? Because the wavelength reduce, the frequency increase. Now, if the ambulance with the sirens, where the siren sound moves 100 km per hour, the observer will hear the sound much higher. The frequency is higher than previous. We notice that the distance between the wavelength considered is very, very short. Meanwhile, the frequency is very high. What happens if the ambulance moves in opposite direction? So the observer will hear that the sound, the frequency of the sirens of the sound become lower. We can notice that the wavelength of the sound heard by the observer is much longer. Longer wavelength with lower frequency. Okay, so now we notice that the sound, if the sound from the siren are stationary, the ambulance are stationary, and the observer also stationary, means well, both of the sound and the observer which are stationary and the relation motion are 0 ms -1. No relative motion means well, the sound heard by the observer will be in the original frequency of the siren. Now we look at that. When the siren is moving, okay, means well, the ambulance move with a speed of v. Where the sound wave vs is a sound wave will move with the speed of the sound, speed of the v minus the speed of the sound. So that means that this speed will change. The sound wave, relative heard by the observer will become higher, okay, because of the higher frequency. So from here, if the ambulance is moving, means well, the frequency heard by the observer will be changed. If the ambulance move away from the observer, where the sound is moved, the sound and the ambulance will move in this direction. Okay, so the sound which hear by the observer, the relative speed of the sound still in the direction of the observer. So that means that these are the relationship between the V and the V source. When an ambulance approach to the observer, what happened is, let's say, the actual wavelength is given by lambda equal to V over F. Let's say is 330 ms-1 for the original sound wave. The frequency of the sound is 500 Hertz, which the wavelength is 0.66 meter. That is the actual wavelength where the sound wave is, let's say, the sound wave, that is the original wavelength for the sound wave where the ambulance is not moving. The observed wavelength lambda prime will be equal to V minus Vs over F, where the ambulance is moved in 40 ms-1, same direction with the sound. So when same direction with the sound, that means that the V speed of the sound must be minus the speed of the source. Speed of the source, okay, Vs is the speed of the source, that means speed of the ambulance. So 330 minus 40, but the frequency of the sound still 500. So we get that the wavelength will reduce 0.58 meter. By using V equal to F lambda, the speed of the sound is constant. So now the wavelength observed, when the wavelength approach the observer becomes 0.58 meter, that means we found that the observed frequency is 569 Hertz. That means that from here, the original sound wave is 500 Hertz. The observed wavelength by the observer is equal to 569 Hertz. Meanwhile, we have two frequency here. That is 500 Hertz and 569 Hertz. Ladies and gentlemen, in this case, the pakcik, the observer beside the roadside, at the roadside, heard the sirens from the ambulance with 569 Hertz. Where the driver, how about the driver inside the ambulance? The driver inside the ambulance hear the sound still with 500 Hertz because the driver moved together to the sound source. So this means that the driver in the car hear the sound with 500 Hertz, but the observer pakcik at the roadside hear the siren sound with 569 Hertz. So actually the sound source produced just 500 Hertz, right? Just because of the relative motion. The observer at the roadside pakcik hear that the frequency is higher. Summary. When there is a relative motion between the source and the listener, the frequency heard by the listener is different from the source frequency. This is known as Doppler effect. If the source moves towards the listener, the observed frequency f prime will equal to V over V minus Vs times with the f. That means that the frequency observed by the heard by the observer is equal to V. V is the original sound wave, the speed of the sound, over the original speed of the sound minus the speed of the source, speed of the car, times with the original frequency of the sound. So if the source moves away from the listener, the observed frequency will be equal to V over V plus Vs times with f, where still V will be the speed, original speed of the sound. That is 330 ms-1 or 340 ms-1, plus with the, divide V plus the speed of the car or speed of the source. So from here, this is how we find the relative frequency of the sound when the observer is stationary, the sound source is moving. Again, this formula, these two formula just obeys for the stationary observer, where he or she observe the moving sound. Okay, that's all. So we notice that when there is a relative motion, same thing, the relative motion. Okay, so the source, remember these two formula always apply in the stationary observer with the moving source. Okay, next. We notice that if the sound the student, there is a student is in stationary. When the bell produces a sound, we notice that the frequency of the sound wave are constant. So that means that the number of the wavefront passing the observer is 23. That means that it's 23 wavefront, 23 lambda in 5 seconds. That means that wavefront passed by is 23. Okay, 23 wavefront already passed by the observer, where the frequency heard will be 23 over 5. 23 over 5 is equal to 23 over 5 divided by 5 is equal to 4.6 hertz. Okay, so that means that is 4.6 hertz. So we check correct. Now, what will happen? Observer move towards the source. Again, now the observer move towards the source. The bell is in stationary, produce the constant frequency of the sound. Where when the observer moves towards the source, that means that it will be 27 wavelength passed by the observer in 5 seconds. That means that the frequency will be 27 divided by 5. We get that the frequency now become higher because it's become 5.4 hertz. Ladies and gentlemen, now we observe if the observer move away from the stationary sound source. That means that now the frequency, the wavelength of the sound passed by the observer is 17 only in 5 seconds. That means 17 divided by 5. 17 divided by 5 is equal to 3.4. 3.4. That means that the frequency will become higher than, let's say, the original frequency of the sound source is 4.6. That means that when the observer moves towards the source, the frequency will become 5.4. That means become higher. Where when the observer moving away from the stationary source, the frequency will reduce to 3.4 hertz. As a conclusion, when the observer moves towards the sound, frequency become higher. When the observer moves away from the sound wave, the frequency reduces. Let's look at the police car. The police car sound source, let's say the sound source is produced, the siren sound is produced by the police car, which is in the stationary position. Again. Now the motorcyclist is moving as an observer, is moved towards to the source. Means that observer move towards to the stationary sound source. What happened is the frequency heard by the observer is higher than the frequency heard of the sound heard by the police in the police car. Ladies and gentlemen, when the listener moves towards the source with velocity v0, the velocity of sound relative to the listener is v plus vo. V is the speed of the sound. Vo is the speed of the observer. The wavelength of sound does not change. Lambda equal to v over f. Therefore, the observed frequency is given f prime equal to v plus v0 over lambda, where f prime is equal to v plus v0 over v times with f. So the observed frequency is higher than the actual frequency because the v plus v0. So that means that there is an increase in the relative motion. So the increase in the relative speed cause the frequency of the sound, original sound wave become higher. Ladies and gentlemen, now we observe again. Again. You notice or not? The siren heard, the sound heard by the motorcyclist is from soft to loud when it approached the police car. When the motorcyclist exactly in front of the police car, he hear the original frequency sound of the siren. That's me at this point. When the motorcyclist passed by away from the source, he will heard that the siren become low frequency. Let me show you the example. When the motorcyclist approach the source, the frequency will increase. Okay, when it's exactly in front of the police car, he will hear the sound, the original sound, original frequency of the sound. When he move away, he will hear that the frequency become lower. For example, if the siren sound produced, let's say, the original produce is e-o, e-o, e-o. For example, when the siren produce e-o, e-o, e-o by the police car, when the observer from far away approach or towards or near to the police car, the observer will hear that the siren will be slightly higher frequency, that is e-r, 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 like that. But when the observer exactly in front of the police car, the frequency of the sound become e-o, e-o, e-o. After that point, that means that when the observer starting away from the, move away or move further from the police car, the observer will hear the siren, the frequency of the siren become beep-o, e-o, 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 e-o. So there's a difference. So look at the deviation. When the listener moves away from the source with velocity v0, the velocity of sound relative to the listener is v minus v0. The wavelength of the sound does not change, where lambda equal to v over f. Therefore, the observed frequency is given by f prime equal to v minus v0 over lambda, where f prime equal to v minus v0 over v times f. The observed frequency is lower than the actual frequency when he moved away. Now, when the listener moves away from the source with velocity v0, the velocity of sound relative to the listener is v minus v0. The wavelength of the sound does not change, where lambda is equal to v over f. Therefore, the observed frequency is given by f prime equal to v minus v0 over lambda, where the observed frequency f prime equal to v minus v0 over v times with the F. The observed frequency is lower than the actual frequency. So when the listener move away from the source, the observed frequency will lower than actual frequency. As a result, the movement of the source will change the observed wavelength of the sound wave. If the velocity of the source is Vs, the car, and the velocity of the sound wave is V. When the observed wavelength is given by lambda prime, let's say we want to find the lambda prime equal to V minus and plus Vs over F. What is the meaning of negative Vs? Negative Vs when the source moves towards the listener. When the source moves towards the stationary listener, so we use negative Vs. If the positive Vs when the source moves away from the listener. That means we use positive Vs. Next, the movement of the listener will affect the velocity of sound relative to the listener. If the velocity of the listener is V0, then the relative velocity of sound is given by Vr equal to relative velocity equal to V plus minus V0. Plus V0, V plus V0, what is the condition? V0 is positive, is plus when the observer moves towards the source. Or move away from the source is negative V0, VO. Okay, sorry, VO. Therefore, if both of the source and the listener are moving, okay, if both of them move towards each other, that means that, for example, F prime equal to V plus minus V or V observer, speed of the observer, over the sound minus plus V source times with the original frequency of the sound. So that means that same thing, VO is positive when it's approach each other. When the two sources, the sound and the observer, approach each other, that means that it will be F prime equal to V, okay, approach each other. So plus V0 because towards each other, towards means that it will be V minus Vs minus because the source move towards the listener. So that means if both of them towards each other, that means that F prime equal to V plus V0 over V minus Vs times with frequency. If the sound source, both of them move in opposite direction or move away each other, that means that F prime will be equal to V minus VO, observer move away, and divide by V plus Vs because the sound source move away from the listener, and need to times with the original frequency of the sound wave. So from here, okay, we can say that as a conclusion, no matter the first formula for the lambda or for the frequency, the information of the positive sign and negative sign plus minus signs for the Vs or plus minus sign for the VO, all of them are obeyed in the frequency, the formula for the frequency. Ladies and gentlemen, as a conclusion, we can say that when an observer moves towards a sound source, the frequency he hears is greater than when he was stationary. When an observer moves away from a sound source, the frequency here is less than when he was stationary. The general equation for frequency is F prime, where is equal to V plus minus VO over V minus plus Vs times with the original frequency of the sound. Ladies and gentlemen, I give you an example in our daily life. Sometimes at highway, we move opposite direction with an ambulance. That means that before the ambulance approach us, we already can hear the sound of the ambulance. That means that when we move opposite direction with the ambulance, the frequency of the sound wave we heard, the siren is with higher frequency. When exactly we are side by side with the ambulance, we will hear the original frequency of the sound wave. Actually, the higher frequency and the original frequency of the sound wave very difficult to differentiate. Seem non-difference, but actually yes. But there is a very clear difference when the ambulance move away from us. Okay, so now we are moved in opposite direction. We heard the sound beep-paw, beep-paw, beep-paw. When exactly side by side, we heard the sound beep-paw, beep-paw. But when the ambulance move away from us, we heard the sound, it becomes beep-paw, beep-paw. Again, okay, I combine the three frequency of the siren, approach each other side by side and move away. We'll heard the sound like this. E-oh, 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 e-oh. So that are the difference. Okay, so this what, okay, next time when you meet an ambulance, so try to observe the sound and relate it with the concept we learned today. So, ladies and gentlemen, okay, that's all for the lesson for the Doppler effect. So here will be the question for the okay, this is the let me say the this is the question for the exercise. Question 1 and question 2. Next, question 3, 4, and 5. Next, question 6 and question 7. Ladies and gentlemen, allow me to show the answer for the question. The worksheet solution or the answer for the question 1. Answer for question 2. Answer for question 3. And the answer for question 4. Answer for question 5. Answer for question 6. Answer for question number 7. Okay, that's all for today's lesson. Thank you very much from me and hope you enjoy the lesson of physics. Thank you very much and see you next lesson.